Okay, so we're going to continue our discussion in section 8.3. We talked about the kinds of functions that we're going to be dealing with in Math 96. We talked about linear functions as a category of functions, and then we also talked about the category of nonlinear functions. And then in the previous video, we discussed a very specific type of nonlinear function called a piecewise defined function. We talked about our cell phone cost plans and how that was an example of one. Well, now we're going to move on to the kinds of things that we can do with all of these functions, not just piecewise, not just nonlinear, not just linear, but all of these kind of functions. We can shift them, and then we can reflect them. And I'll sort of illustrate what both of those concepts are instead of trying to explain them verbally. All right? So what we'll do first is we're going to take a linear function, and we're going to talk about how to shift it. All right? So I'm just making a function up. Actually, I'm not even going to make it up. Super easy. Y is a function of x and it behaves like x. So what do I mean by that? If we were building our tables, I would use the same strategy as I've used in previous videos, where I know that y depends on x. So if x is 1, I just plug it into my function. Well, y equals 1. I should say y is a function of x just to keep it clear. And you can imagine how this is going to go. -1, -1, okay? And then the same strategy that we've been using, after I build my table values, I turn those table values into ordered pairs, then I plot those ordered pairs on a coordinate system, and then I draw my shape. I'm going to skip a bunch of those steps because it's really easy to see what kind of shape my graph is going to take. It's going to be a 45-degree angle line that goes off like this. This is the graph of the function y is a function of x and it equals x. Okay? And I should say, just for clarity's sake, this function goes on for negative infinity all the way up to a positive infinity. There's no number that I can put in here where I get an illegal value for this function. So, this is good for illustrating purposes. Because which way can there are two shifts that I can make to it. I can shift it either left or right, or I can shift it up or down, couldn't I? I could have a function that is has the same slope, but is just shifted up, and it would kind of look like that. Or if I wanted to shift it right, I would have a line that looks maybe like this. So how would we take this idea and turn it into an algebraic representation of what we're talking about? We're going to have to use a different function notation. So what I'm going to say is that y is a function of x, but now I'm going to craft a function called g of x, which will represent the shift. So what I'm going to do is I'm going to shift my function up by 3. All right? So what I'm saying is g of x is my new function. It also depends on x. And the way that we get there is by taking my original function for x and adding 3 to it. That's what we're saying with this symbol notation. So in this case, what I'm going to do is I'm going to take my relationship between f of x and x, and I'm going to replace this in my setup. So my new function is x plus 3. Okay? All I've done is I've said y is a function of x and it behaves like x. I defined my original function. And then I set up my new function to say, well, it's a shift of my original function. And I'm using the fact that I want it to shift up. And I'm saying we're going to take my original function and we're going to shift it up by 3. And that looks like exactly what you'd think. I'll kind of leave a little ghost of where my original function was. This was my f of x. My g of x is going to be up 3, but it's going to have the same slope. It's just now shifted up by 3. G of x equals f of x plus 3. And if I were going to shift it down, guess what sign would change? The sign that would change would be the addition sign. instead of adding 3 to it, I'd be subtracting 3 from it. So the general form of a vertical shift, we say our g of x, our new function, equals our original function plus or minus, and we're going to say k. K represents a number. And we say that when we are when we're adding k, so when we have f of x plus k, it's a vertical shift up. Well, we'll say vertical means up, so we're shifting up. And when we have it in the form f of x minus k, we have a shift down. Okay? Those are good things to have in your notes, or if you want to go back and capture that, I feel like that's a good thing to have in your notes. So that handles the up-down shift. Now we need to talk about left-right shift. And to do that, we're going to have to change our function a bit, because it's not going to be exactly clear what's going on with this linear function. Because I could just as easily say that x plus 3 represents a shift to the left, right? If this is my original function, because it's a line, I've shifted it up, but I achieve the same thing if I shift it to the left. Okay? So that's why we use linear examples to talk about vertical shifts, and when we talk about horizontal shifts, we have to use nonlinear functions to illustrate it just a little bit clearer. All right? Keep this in mind though. My function has a dependent variable, and then after I perform this function, I add some number to it, okay? That's how I get my vertical shift, by doing this function first, then adding a number. You'll see why I made that point in just a second. Now we're going to use a little bit more of a complex function, a nonlinear function, but not too difficult of a function, particularly for 96 students. So y is a function of x, and it behaves like x squared. Okay? I think we did this in one of the previous videos where we graphed it. So I'm not going to go through all the tables. If you want to see the table work and the ordered pairs, you can go back to, I think it was section 8.2, and watch that video. So on the y and the y equals fx axis, what we have is an upward-facing parabola that goes like this. And, you know, just for, I guess, consistency's sake, I'll say that this is the point, -1, this is point 1, and then this is 1 here. And I'll just illustrate. I know some professors want you to put the arrows on the tops of the graph so that you know that this function goes on forever. So how would I shift this function? Up or down or left or right? Well, we talked about how to shift it up or down, but now we're going to talk about how to shift left or right. The way that we do that is by putting an addition inside our function. So if I were to say g of x is a change in our original function. It's a shift of our original function. And I want to shift it to the right by 2. I have to put this shift inside my function notation. Last time we had our vertical shift was on the outside of our function notation. Horizontal shifts are always inside function notations. The reason why that's not very clear to see in linear functions is that we can drop the parenthesis right away. In this example, let me show you how it works. So if I wanted to shift this function by 2, I have to replace my original function with my shift. So I move from, instead of x squared, now I'm x minus 2 quantity squared. You see, that's a little bit different than the linear thing. The linear thing looks almost exactly alike. This will not give us the same example. If I did, for example, if I did x squared minus 2, it's not the same. This is not the same as this function right here. Okay? So when we plotted, so we know that this is a parabola and it's upward shape. The shape's not going to change. We're just saying that we're shifting it to the right. So we would move to the right by 2, and our new shape would be the exact same shape as our parabola, just shifted to the right. So in general terms, what we say is that if g of x represents a shift of our original function, our shift must be inside our function notation, our original function notation. And unfortunately, it's just the opposite with the sign. So when we're saying x minus h represents a shift to the right, and f of x plus h represents a shift to the left. The reason that this is true is apparent when you start plugging values into your sets of equations. So if you start with a table for your original function and you start listing table functions and you set that same table up and you write out a table of x and your new function, let's say it's f of x minus h, you will see your values are shifting your ordered pairs to the right. The values that you get will be different. Other than taking all the time to go illustrate that, there's really no other explanation. So just recall and remember that when we're talking about vertical shifts and x minus h, where h represents any number, this subtraction represents a shift to the right, and when you add these two quantities together, it represents a shift to the left. All right? So we've talked about horizontal shifts and we've talked about vertical shifts, and we can have a combination of both. So not only can we have a shift to the left and right, but also a shift up or down. And again, with nonlinear functions, this is pretty easy to see. So what if I wanted to take this original function, x squared, and not only do I want to shift it right, but I also want to shift it down. So I say I want to shift it down by 3. So I want to put it down here. Well, I used the trick that I used for my linear shifts when I was talking about how to shift a linear function up or down. And I would just add, well, in this case, I would subtract, wouldn't I? I would subtract k. So in this concrete example, what I would say is my new function represents a shift of my original, right? My original, I'm going to shift to the right by 2, and then I'm going to shift it down by 3. And then I have to replace my function notation with the actual algebraic representation of my function, which is this. Take this quantity and square it. So I have to say my shifted function is now the quantity x minus 2 squared minus 3. Now, I can leave it like this if I want to talk about how to see my shifts. Now, you might be given a version of this function where it's already expanded out, and you have to convert it into this form so that you can see where the shifts are in your function. So we'll talk about how to do that maybe later. But this is just getting used to the concept of shifting functions. We have one more thing to talk about, one more thing that we can do to functions. Instead of shifting them left or right or up or down, we can also reflect them about the axis, or the axis. What do I mean by that? What does it mean to reflect something? Well, I mean, it really does mean exactly what you think. So if I were to have a function, and we'll use our good old trusty f of x equals x squared, and we start with this function. If I wanted to reflect this about the x-axis, it means that I want to see the shape that it takes when I hold a mirror up to the x-axis. So imagine if I had a mirror pointed along the x-axis and it was just this function, but it was only pointing on the opposite side. It would have the same shape, but imagine its reflection in a body of water, right? It would see itself doing this, wouldn't it? Okay? So how do we write this idea algebraically? What we say is that the reflection of a function about the x-axis, because there's another way to reflect this about the y-axis, right? Fortunately for us, this function is reflected about the y-axis, and we want to see it shifted about the x-axis, so we want to do that. What we say is that g of x represents a reflection of our original function, f of x. This is always true. This is the standard form of this. So let me prove it, okay? I'm going to use our same strategy that we've been using in our previous sections. I'm going to use my table values for x and f of x. I'm also going to create a third column for my new function, g of x, which is the negative of f of x, okay? So when x is -1, or how about if I do -2, 0, and +2? I get, what's -2 squared? That's 4. What's +2 squared? That's 4. 0 squared is 0. Now, when I'm talking about a negative of my function, I have to be very, very careful. My function is actually x squared. That's my function. But now I have a negative in front of it. In this particular case, I can drop the parenthesis, and I get a function of -x squared. Now, I'm sure you guys have been warned about this particular thing, but I'll bring it up again. This is not the same thing as the quantity -x squared, okay? So, when I'm inputting my table values for this function, -2 quantity squared, and then take a minus of, is going to be -4. And the same thing with +2. 2 times 2, or 2 squared is 4, and then I have to stick a minus sign in front of it. So I get a -4 here too. And 0 is still 0. So when I'm making ordered pairs of this, I get the ordered pair -2, 4, 0, 0, and 2, 4. And when I plot those on the graph here, this would be my 2. Well, let's see. This would be my 2, and this would be my 4. This would be my -2, and this would be my 4 up here, right? 2 and 4, and -2 and 4. We can see, oh, I'm getting my original function. I'm getting my shape that moves up. And when I build my ordered pairs for my shifted, or I should say my reflected function, I get the point -2, -4. I get the point 0, 0 again. And I get the point +2, -4. When I plot those points go down here, right? 2 and -4. So my shape isn't really right, but you get the idea. Let's see. So 2 and 4 is probably right around here. 2, 4, right around here. Because my y-coordinate in both cases is negative, I can see almost right away that my shape is a reflection of my original function. In my head, it looks a lot better. Okay? I know that was a lot of material to go through. We were trying to condense this stuff into, sizable chunks. So feel free to stop the video at any point and go back if I explain something too quickly and you need to go hear it again. Please do that. But that is, in a nutshell, how to start working with shifts and reflections of functions. And I encourage you to start playing with the examples in the book and using the same sort of strategies that we have in the video. There are a lot more complicated versions, but the steps are exactly the same.